So in continuation to our previous class, we were till here in our previous class. Okay, right. I just want to give you a situation where, for example, you have a material. You can consider that this is a ball made of isotropic dielectric with dielectric constant Q. You just have a point charge Q. What they want is find polarization as a function of vector r bar relative to center, which means at that point I want polarization. What? Also I want bound charge inside a sphere whose radius is less than the radius of the ball. Fine, no issues for me. The only part that I would believe is I will enclose. Gazala is also the same way. You are taking a shell of some small r radius, and you want this is r bar. R bar. We will apply Gauss at this point. At this point, in this case, please help me in writing Gazala properly. Gazala dielectric constant times E net into 4 pi r square is 1 by epsilon naught times Q free. Any student having doubt on this? Boys and girls? Sure. Dielectric constant E 4 pi r square 1 by epsilon naught. What is the field charge here? This allows me to write E at that. 1 by 4 pi K epsilon naught Q by R square. Are we clear? Just want to ask you one single question at this point. What is P bar? గట్టిగా చెప్పురా హారిక చెప్పు. P bar అదేలే పోలరైజేషన్ వెక్టార్. దిస్ ఈస్ susceptibility into epsilon naught into susceptibility is again polarization vector. What do you want? Bound charge. Or you are not asking out, you are asking in. That's not given. So this is nothing but is this fine? Any doubts? Boys and girls, are we clear? Any doubts? Sure. Last student. Again, recall the formula once again. Integral P bar dot ds bar is equal to Q bound out. Integral P bar dot ds bar is equal to minus Q bound in. ఇంకోటి sigma bound is equal to P bar dot n cap. P bar is susceptibility epsilon naught E bar. I am using only these again. There is another thing which you can also use. The same thing which you are using here can also be in vectorially. You said ds bar. Vectorially, you can write this in another form. Notice left hand side you have volume integration. Notice right hand side you have so to link these two, there is a theorem in vectors, divergence theorem, cause divergence. So by applying that, you will get a condition called any doubt. Even in fact, Gauss law can also be written like this only. In the absence of dielectric. Okay, na? Right. So this is also one important relation which you might use, but rare, very rare. Remember here, when I am writing minus in the sense inside, bounded inside. Right. Next condition. Sometimes, అంతే del bar అంటే see, it depends again. Good question that you have asked. It depends again on what you are using as the coordinate system. In a polar coordinate system, in a Cartesian coordinate system, we will write del bar as dou by dou x of okay. Whereas in cylindrical coordinate system, spherical coordinate system, it is a different. One question we will have in the same thing uh, in Irido question. That time, all of the students went wrong by just simply writing dou by dou. So actually, you are not supposed to write. See, when I am using Cartesian coordinate system, x, y, z were the coordinates. When we are using spherical coordinate system, you know what we will use spherical coordinate system or theta phi. Okay, this is written as and this is interesting. So I'm not sure to what extent that we use this one, but as I mentioned, very rarely, even though we will use, but it is good that um, you apply, you know this at least. For example, if A bar is some vector given like this in spherical coordinate system. In spherical coordinate system, if it is given as A r cap, like AXI cap, A theta cap, A Good that you asked this question. Actually. Because I felt that you people have some idea on this. Because 3D geometry అయిపోయిందా మీకు? Because it's not completed, it is my duty just to at least give you idea. Now, is given as 1 by r square dou by dou r of r square ar plus 1 by r sin theta dou by dou theta. Even just remember, I will give cylindrical coordinate system also. అరే యూజ్ చేస్తారా లేదా అలాంటి ఒకటి ఉంటుందని తెలియాలిగా కనీసం మీకు. రైట్, నెక్స్ట్ ఏ థీటా సైన్ థీటా ప్లస్ 1 by r sin theta dou by dou phi of a5. Whether I use or not, that's a different story. Any doubts now? How to apply again? What is del and all that you will learn that. This is not the time to learn that. Right. Next thing, cylindrical coordinate system. We are dealing del operation in cylindrical coordinate system. So what are cylindrical coordinate system? You use r theta phi there. Here you will use r phi z coordinates, x, y, z place. You know already. Azimuth angle, actually, one is right. Here also del bar is equal to same, imitating like as if that I am writing the same thing. Those it. Or radial distance. Here the angle is azimuthal angle and z stands for the height. Okay, this is azimuth angle. Right. So now I am taking the same thing. A bar is some vector defined as AR r cap plus A phi phi cap plus A z z. Now when you apply divergence to this, del bar dot A bar is equal to del bar dot A bar is equal to 1 by r dou by dou r times AR plus 1 by r dou A phi by dou phi plus dou A z by dou z. Majorly, they are not difficult. The problem is I couldn't draw box. He is not accepting that box. I'll draw my own box. Right. Okay. Why? Because see, when I was discussing to your senior, when I don't remember, waited, I didn't get a question answer properly. Written again, didn't get answer properly. Then I have corrected myself. Therefore, just keeping that point in view, you don't require the first part. That already I have habituated to that in electrosec. These two are different. Only information. We don't use it regularly, but just require information. Right. Next thing that what we are going to do is some conditions to be discussed. Some conditions to be discussed. With this, I'll close the thing. These are called boundary conditions. Okay. So with this, the theory part is done, and thereafter I will deal only problems. That problems I will deal it on more. No, I'll stop. Boundary conditions. What is your problem with the boundary condition? Now I am facing a dielectric boundary. The entire portion the lower portion is a dielectric. The above portion is air. Okay. So you are facing a boundary here, air dielectric boundary. Now dielectric constant, say for example, here is a K1, of course one. The dielectric constant here is a K2. Now you take all like your Gaussian sphere that we will call as a pill-shaped Gaussian surface. That's a Gaussian cylinder. Above dielectric constant K1, below the dielectric constant K2. First point is that First point is that at this point there is no free charge. Not a metal plate. It's a dielectric. There is no free charge enclosed inside the bond. Yes or no? Right. So when there is no free charge enclosed in the boundary, Gauss law in dielectric, zero. So now the question is K1, E1. Remember E1 normal component into ds outward flux minus K2 E2n. Why I'm using a word n? Normal है కదా flux. Into ds is equal to g. Therefore, K1 E1n is equal to K2 E2n. Boys, any doubts? And this is the normal condition. This is boundary condition number 1, normal to the boundary. Any doubts? Clear? Remember, once I am out of this theory, I'll run madly after you with problem. Listen to this theory carefully. Right. What is the next condition? Here I have written normal to the boundary, tangential to the boundary. Now imagine the same boundary here. I'm drawing the same boundary here. And now we don't require a three-dimensional shape, just you require a two-dimensional shape like this. Now in this, E1 tangential, E2 tangential. It's a very small elemental length here. Dielectric constant K1, dielectric constant K2. Okay. Now try to please understand. Now try to please understand. For this closed path, Y. ఇంకొంచెం బాగా చెప్పచ్చు. వై? ఆడపిల్లలు ఎప్పుడు నిద్రపోదాం అని చూస్తాం. ఫ్రంట్ అమ్మాయి ఒక్కతే కొంచెం యాక్టివ్గా ఉంటుంది. హంసిని, హర్షిని. వై? ఈ పొందర కన్జర్వేటివ్ ఫీల్డ్. ఎలక్ట్రిక్ ఫీల్డ్ is conservative. Work done by a conservative field in a closed path is okay. In this process, A, B, C, D. A to B, E1T times DL plus E1N. నేను తప్పు రాశాను, ఎక్కడో తప్పు రాశాను. E1T, E2T, E2T, E2N dy plus E2N minus dy. Why? Because when you go up, the same amount you come down. So that is the reason why I don't want to add even these two terms also. Anyway, they'll get cancelled. Plus C2D which clearly implies always E2 tangential is E1 tangential. E2 tangential is E1 tangential. Any doubts? Boys and girls, any doubts? Next. If the issue is previously what the condition I took is above is air, below is dielectric. Any doubt in this, by the way? Right. These are very important. Very important, I mean. What if instead of all this stuff, you have the boundary above is metal, below is dielectric. Now what is happening over? Yeah, correct. You are taking an elemental cylinder here. You have a metal above and the portion is dielectric below. You know the dielectric will have dielectric constant K. Don't ask me about the metal. Right. And here it is a sigma bound. Here it is a sigma. You know that. What we have done here, plus sigma minus sigma. That plus sigma is sigma, minus sigma is sigma bound. Now, too many number of cylinders for this. Boundary, dielectric, metal is the last theory point, according to. Right. I'll ask you one question straight away. And you know that it is E here. What is E here? Why? Because it is a conductor. Next, sigma, sigma P. So now integral E bar dot ds bar is Q enclosed by epsilon. This is the general formula of gas. So minus EDS plus 0 is, boys and girls, sigma plus చెప్పునా చేయొచ్చు. No issues. No issues. So therefore we know E inside the dielectric. We know E now. E is nothing but minus sigma plus sigma bound by epsilon naught. That's fine. Next. Now, what is that we are finding here is, if I am using Gauss law in dielectrics, K E bar dot ds bar is sigma times, if I am applying Gauss law, Q free. Okay. So E is sigma by K epsilon. Both are E's only. It is the same E, in fact. So therefore, what we already know is sigma by K is minus of sigma plus sigma B. So sigma bound is, okay, minus sigma times 1 minus 1 by K. And we already know this. That's the boundary condition. With this, I'll close the thing. So we will start applying properties.